Now this is a fellow by the name of David Green. He's at Cambridge. And he has the catalog of the supernovas. And the latest number of supernovas that he's got is 295. That doesn't focus too well. Is that really focused? Let's see if we can get that focused a little better.
They're not going to be able to see it regardless. It's a little small. Don't worry about it.
That's 295 is the number right there. 295 supernova remnants. 295. This is on the internet. You can check me out. It's at the Muller Radio Astronomy Observatory in Cambridge. And this number 295 is kind of interesting. The last time he did a catalog, see this is 2000. This is the 2017 catalog. The 2014 catalog had 294 of these supernova remnants. So they only discovered one supernova remnant in 3 years, between 2014 and 2017. They only added one to the catalog. So they're getting very close to finding them all. So this number of supernova remnants in the galaxy is probably close to the real deal. Okay. For more than 100 years, astronomers have been watching supernovas go off on the galaxies. And from that, we can estimate that a normal galaxy like ours should have a supernova go off about 3 per century. Now, the last one that we know of was not the one in 1604, but one a couple of hundred years ago. It was inside the nucleus of our galaxy, and it can't be seen with the naked eye. It can't be seen. It's only visible with the radio telescope. But it was just a couple of hundred years ago. Now, 3 per century is a good estimate of how often these things go off. That means every 35 years, plus or minus 7 years, you get one of these supernovas. Okay. Now, if we combine the results, what do we get? Supernova remnants, we've got 295 of them. Can you multiply 295 times 35? I did. And I got 10,300. That's the age of the galaxy according to the supernova remnants. The number of supernovas that go off in the galaxy is about 3 per century. There are 295 of them. So we multiply 35 times 295 and we get 10,300. Now this is uncertain by about 3,000 years. So it could be older than that. It could be 12,000 years, like I say. If the galaxy were old, very old, if the galaxy were millions and millions of years old, there should be 100,000 to 1 million supernova remnants. And indeed, the galaxy would be Swiss cheese. These supernova remnants would be overlapping each other and making holes. And that's what I used to think. That's what I used to think when I thought of Star Trek, that those guys were finding ways to go from one supernova hole to another. That's what I thought. Now, to explain the missing supernova remnants, a few astronomers have suggested that the Milky Way is a very peculiar galaxy, having drastically smaller numbers of supernova-ready stars. But that's not reasonable at all, because we're measuring these things going off in other galaxies. Why not here? Now, we've now given 2 credible evidences for the age of the Earth, haven't we? The winding up of the galaxies and the supernova remnants. And I gave you some other stuff as well. Okay? So this is evidence that our Milky Way is very, very young. Thousands of years old, not millions, not billions. Thousands of years old, not millions, not billions. Our galaxy is indeed very young. The Earth can't be old. Can you have an old Earth inside of a young galaxy? No way. The Big Bang is a big mistake. This is one of the things that I'm going to talk about. The Big Bang is a big mistake. There are three pillars that the Big Bang stands on, and they're all falling apart. Okay, what are the pillars of the Big Bang? A model for the creation of the chemical elements. They have a model for the creation of chemical elements. And two, alleged cosmic microwave background radiation, which they think is really wonderful. And three, the supposed cosmic expansion, the idea that the galaxies are moving away from each other, and that's called cosmic expansion. Now, they all have fatal flaws to them, and we'll show you one at a time. Now, the Big Bang has no known mechanism for making heavy elements. There is no method that the Big Bang has for making heavy elements. And there's no other known mechanism. People have suggested recently that it was neutron stars colliding, but that doesn't seem to work either. They've tried a lot of things to try and make this work. But all the elements heavier than bismuth are unstable. They're radioactive. They split apart. Uranium splits apart. Plutonium splits apart. Thorium splits apart. Radium splits apart. They all split apart. Well, if they all split apart, then how do you make them? Well, the mechanism that has been proposed by the scientists is massive neutrons. A massive bombardment of neutrons on a nucleus, existing nucleus. And that massive bombardment of neutrons, all of the neutrons are decaying and making, some of them making into protons, which makes the new element. The problem is that there is no place in the known universe where you can get enough neutrons in order to make this work. Okay. The Big Bang also struggles to explain the measured abundance of certain light elements. For example, the abundance of lithium is a factor of 3 to 4 times less than the Big Bang model predicts. And helium also has stars with very low, there are stars with very low helium abundance as well. So the abundances of the elements is not something that is a good, is not doing well for the Big Bang. They advertise and they say, oh yes, it's doing wonderful, because it will explain helium-3 and deuterium and these other things, but it won't explain some stars have very low helium abundance, some stars have very low lithium abundance, and most stars have low lithium abundance by a great factor, much farther than they can explain. Now, this is the alleged cosmic microwave background radiation. It's supposed to be the radiation left over from the Big Bang. The Big Bang radiation expands, and after 3.7 billion years, it arrives here. There's a real problem.
Dr. Harris, it may be of value for people to understand that that is a heat map
Yes.
of the entire universe, and it is measuring very cold temperatures.
Oh yes, I'll get to that.
And the whole difference between the red and the blue is less than a degree.
Well, it's much less than a degree.
Much less than 1 degree.
It's, the main temperature is 2.725 Kelvin. This temperature, the whole thing, averages 2.725 Kelvin. And the variation is much less than 1,000th of a degree. Much less than 1,000th of a degree. The alleged cosmic microwave background has such serious problems that we're not even going to bother to spend much time on it. The cosmic, it is too uniform. What does that mean? It means the temperature one place is about the same as the other, is about the same as the other. It's all the same. It's all the same. Now, in order for the universe to form galaxies, you have to have irregularities. You have to have a dense region and a low density region, and you have to have a clumping occurring. Well, that clumping isn't happening because the temperature differences are very, 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 very small. And so this leaves no seeds for galaxy formation, let alone forming galaxy clusters or superclusters. We know that galaxies are in clusters, and we know that galaxies are in superclusters. But the microwave background radiation doesn't even give us the ability to make galaxies let alone clusters of galaxies, let alone superclusters of galaxies. Now, one of the interesting things about this is that there's a dipolar pattern. Notice, this dark line here is the Earth's orbit. The Earth's orbit on the sky. And it divides the cosmic microwave background into two sections, a cold region and a hot region. This is the, what is that? That's the, I'll look at it on here. That is the equinox. Which equinox? That's the fall equinox. This is the fall equinox. This is the spring equinox. Okay? Now, why should the Earth's orbit divide the cosmic microwave background radiation into two pieces? A cold region and a warm region. Okay? The dipolar pattern of the cosmic background is perfectly aligned with the Earth's orbit around the Sun. Now, the astronomers hate this idea. They hate it with a passion. They call it the axis of evil. Why? Because it brings them back to the fact that this is not real science. This is not indicating that this is the Big Bang. This is not an indication of the Big Bang at all. Not at all. Okay. Now, the Big Bang, this is the third aspect of the Big Bang. What did I tell you about? Formation of the elements didn't work. Cosmic microwave background doesn't work. Now we're going to talk about the expansion of the universe, so-called. Now, the Big Bang cosmology supposes that there is a general expansion of the universe as shown by redshifts of galaxies and quasars. Now, we're going to start with, to make a redshift clear, we're going to start with, this is a very interesting thing here. Have you ever heard an ambulance go by? The frequency is high when the ambulance is approaching. It's low. The waves are farther apart when it's receding from you. So that's called the Doppler effect. We talked about that a little earlier. Now, this is the Doppler effect. Now, the same Doppler effect works with light. If the object is moving away from you, moving away, the waves are spread out and you get a redshift. Shift towards the red portion of the spectrum. If you have an object that's moving towards you, it gives you a blue shift. And the light is shifted towards the blue. Now this is a spectrum of several objects. A star nearby which has unshifted light. A nearby galaxy which has a little bit of a shift. And then a faraway galaxy that has a lot of shift. And this is called the redshift. If light is spread out into its colors in a spectrum, the receding movement is shown by the redshift. Now, astronomers have an abbreviation for the redshift called Z. Z. They find it Z. They call it Z. Z is the velocity of the object's movement divided by the speed of light. It's a fraction of the speed of light. So Z is equal to V over C, the velocity divided by the speed of light. These are always recession velocities because when you get far enough away, everything seems to be receding. You know what it looks like. The Big Bang model has Z. The Big Bang model has, for local objects, for nearby objects, the Z is less than 1/10. So that means it's objects nearby are moving at less than 1/10 of the speed of light. Now, the problem comes when you actually look at galaxies nearby and you see objects with high redshifts right next to them. Very close. See this? See that? That's 1 minute of arc in the sky. That's the smallest thing that you can see with the naked eye. You can only see 1 minute with the naked eye. 1 minute, 1/60th of a degree. That's what you can see with your naked eye, is 1 minute of arc. And that's what that is, 1 minute right there. So these things here are closer than you could see with your naked eye. And notice that we have the normal galaxy, which has a Z of 0.029, very small. But we have an object down here, which has a Z of 0.391, and another one of 0.243, and another one of 0.057. Now, if this was true, 0.057 is just about twice that. So this object would be twice as far away as this thing. But they're right next to each other. These things are right next to each other. Some nearby galaxies have Redshift quasars connected to them, physically connected to them. Now here's some other stuff. Anomalous redshifts. Okay. Here we have a galaxy, which is a redshift of 0.018, and a quasar, which is a redshift of 1.17. That's movement. That's really hauling. These are not just random alignments. There are too many of them. Here's another quasar that's one redshift greater than 1, and a galaxy that has a redshift of 0.0288, very small. So you've got these objects that are obviously nearby, according to the redshift law. The redshift law says the greater the distance, the greater the redshift. The greater the distance, the greater the redshift. Well, this thing should be at the edge of the universe. This thing should be right next to us. And they're right next to each other and they're connected. Now, what I'm going to show you here is something that might be confusing for you. This is the redshifts of all the galaxies in a cluster. Now, every one of those dots is a galaxy. Every one of those dots is a galaxy. Now, the cluster is supposed to be right here at 0.08. But notice that you've got clumps, 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 and clumps. Clumps, 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 clumps. What do you got? Clumps. Now, the clumping is an indication that what we've got here is not real motion. Now, the spreading of this thing up here, that's an indication of maybe a little bit of movement. There's a difference between there and there. That's about as much movement as the galaxies are really showing. They're really showing that much movement. But the clumps are all separated by something that indicates that the galaxies have what's called an intrinsic redshift. Wow, intrinsic redshift. The redshifts show clustering about certain values. This shows that there is an intrinsic, built-in, not cosmic redshift. That the redshift is something that is part of what's going on inside the object. Wow. The behavior of measured redshifts shows that redshifts are intrinsic, not cosmic. Not cosmic. Not due to extinction. Not because of the Big Bang, but because of something going on as a mechanism inside of the galaxies. This destroys the Big Bang entirely. So we have now seen all 3 pillars of the Big Bang destroyed, and we now have seen 7 reasons why we should not believe that the Earth is old. We now have 7 reasons to believe that the Earth and galaxy are young and created, not old and evolved. Now, so we've talked only about astronomy so far, so let's do a little bit of something else. Okay? So let's further explore the best science to find the true age of the Earth. Now, that's people, folks. Lots of people. A powerful clock is the human population growth. Now, if you start at 2 people and you double the population every 1,000 years, a very, very, very slow doubling time. Can you divide 1,000 into 1,000,000? What do you get? You get 1,000. So that's 1,000 doublings. And 1,000 doublings means 2 to the 1,000th power. Which happens to be 10 to the 302 power. 10 to the 302 power. Now that's many more times than the number of atoms in the universe. Isn't that fun?
And there's
If you have a population starting out at 2 and you double every 1,000 years, long time, you get in 1,000,000 years a population bigger than the number of atoms in the universe. That's unreasonable. It is very unreasonable. A reasonable model of human population growth estimates that the Earth must be less than 15,000 years old. Now, these are some of the estimates that we have for the age of the Earth. Formation of river deltas, less than 10,000. 10,000. Sediments going into the oceans, less than 30 million years. Seafloor ooze accumulation on the seafloor, less than 2 million years. Human population growth, less than 15,000 years, we just said. Leaching of sodium and calcium, chlorine from the continents, less than 1 million years. Calcium and uranium into the oceans, 1 million years. Rise of mountain ranges, we actually measure the rise of mountain ranges. We can do that. And we estimate that the mountains are only 1 million years old, at most. If they're rising at the same rate that they are today. They could be rising faster. Copper into the oceans, 50,000 years. Silicon and nickel into the oceans, 9,000 years. Carbonate ion into the oceans, 100,000 years. Helium flow, we're going to talk about that, into the atmosphere, less than 20,000 years. All of these age estimates rest on process rates, which are measured in the present and assume constant in the past. Now, are you surprised that so many of these process rates give us a young Earth age? Yeah, most people are. Most people are very surprised. The combined estimate is less than 15,000 years. Now, there are a few processes, there are very few processes, that give us an old Earth age, for an old estimate for the Earth. And let's talk about some of them. Let's talk about some of those that are used for that. Scientists have produced a variety of models of radioactive decay processes, suggesting that the Earth might be very old. That radiometric dating has serious problems. And we'll talk about 7 problems. 7 problems for radiometric dating. In general, molten rock, as it cools, gives a solidification age. The materials stay the same once you've crystallized them in rock. The radioactive decay of uranium to lead is the clock that is most used to estimate the solidification age of meteorites. The one on the left is big, the one on the right is small. There are at least 7 serious reasons to question radiometric dating. Number 1, the uranium to lead decay method used on meteorites in old Earth models should show similar or nearly identical solidification ages for all the meteorites, but they give instead widely different ages. Okay, the meteorites and the Earth, if they are together at the same age, they should have all the same age. Not so. Not so. The most studied of all meteorites for age dating are the Ionian stones, which experts have agreed solidified 4.6 billion years ago. Now, that's what they say is the age of the solar system. Now, there are different nuclear decay methods. There's different methods for measuring nuclear decay. One is the lead-207 to lead-206. It gives 4.5 billion. The lead-207 to U-235 gives us 5.57. The lead 206 to uranium 238 gives us 8.82 billion years. The lead 208 to thorium 232 gives us 10.4 billion, and the strontium 87 to the strontium 86 gives us 4.48 billion. Aren't those all supposed to be the same? They all should be the same, but they're not. And this is an indication that we've got a problem. Now, the origin of the solar system theory says that all these things came about when objects greater than 50 miles across were assembled in the gas and dust cloud. Remember I told you only the things this big form out of that? Not 50 miles across. Okay, they assume 50 miles across. Okay, so the meteorites, everything that forms in this idea of the solar system should all have the same age. Okay. Now, the age of the Earth and meteorites, but major meteorite ages vary widely from 2.5 to 14 billion years. Oh, that's a problem, isn't it? The ages of the meteorites vary quite a bit, depending upon what method we use. And the old Earth estimates the Earth's age have been doubling since 1925. Now, in 1925, the age of the Earth was thought to be just a little over 1 billion years. Now, we've got the age of the Earth is 4.6 billion years. It went up 1/10 of a billion during the time I've been studying. When I was going to school, graduate school, they said it was 4.5. Now they say it's 4.6. It keeps on going up. The second reason, there are rocks that we know are very young, and yet they have old radiometric ages. For example, a fellow by the name of Steve Austin went to Mount St. Helens after the eruption of Mount St. Helens and grabbed some stuff right off the top of the dome. He's a really adventurous guy. He goes to the top of the dome and he grabs some of this stuff and he sends it off to laboratories all over the Earth. And they give him these ages. What's the smallest age? About 500,000 years. And what's the largest age? 3 million years. So he takes this stuff, sends it to the laboratory, and they say, that's 500,000 years old. Well, he just grabbed it off the top of the mountain. Is it good that these things are so far dramatically wrong? Now these are the volcanic eruptions that we have known, that we know about. Okay? Here we have Mount Etna. When 2,100 years ago, what's the age of it according to their age? 0.25 million years. Mount Etna, 29 years ago, 0.35 million years. Older than the one that's 2,000 years ago. Mount Lassen, 85 years ago, 0.11 million years. Kilauea in Hawaii, less than 200 years, 21 million years. Kilauea, less than 1,000 years, 43 million years. Kilauea, less than 1,000 years, 30 million years. Do you get the idea that they don't know what they're doing? Their ages for things that we know are very, very, very wrong. Third reason, different radioactive decay processes give us different ages for the same rocks. Now, the Grand Canyon has volcanic rocks on the bottom and volcanic rocks on the top. Now, the top rocks have older ages than the ones on the bottom. Doesn't make any sense. These are the ones for the rocks on the top. Notice that they vary in age from 0.01 to 117 million years for the potassium argon age. The lead-lead isochron age is 2,600 million years. That's quite a range of age, isn't it, depending upon which method you use. The average is 1.3 billion years. The ones on the bottom vary considerably as well, but they're average 300 million years younger. The ones on the bottom average 300 million years younger. Now, here's a number. These kinds of problems are occurring all over the world. Okay? Mount Nadanor where is that?
New Zealand.
Let's see. Nadanor let's see.
New Zealand.
New Zealand. What's the variable ages? Less than 0.27 to 3.5 million, 153 million, 3,900, depending. See, notice the lead ages always get very old ages. So this is happening all over the world. Now, when the first lunar rocks were brought back, this is what you were talking about earlier. A variety of radiometric ages were attributed to them, all the way from 2 billion to over 14 billion years. They couldn't settle on the age of the rocks. Why? Because they didn't know what that was supposed to be. Because these radiometric methods don't really work at all. They only give you a guess. The unreliability of the radiometric method is demonstrated. Okay, reason number 4. When these radioactive processes occur, they release helium. Okay? Nucleus decays, it releases an alpha particle. An alpha particle is a helium nucleus. Now, when uranium-238 decays to lead-206, it releases 8 alpha particles. Most uranium is found in zircons. Zircons are tiny crystals inside of the granite. Okay? The 8 alpha particles become helium atoms. Now the helium atoms should escape the rocks and go into the air. The old Earth view says that great quantities of helium produced by radioactive decay should have escaped into the atmosphere. So the atmosphere, our atmosphere, should be mostly helium. But helium is not in the air, the helium is still in the zircons. In fact, there's good reason to believe that helium doesn't escape from the Earth's atmosphere. Helium does not leave from the Earth's atmosphere. It's too heavy. In fact, the helium is more abundant at the top of the atmosphere than it is further down. If you have a gradient of something escaping, it has to have a higher abundance lower than it does upwards. It has to have a higher abundance below and a lesser abundance above if it's escaping. But that's the reverse of what we see here. We have the helium is higher in abundance at the top of the atmosphere than it is below, and the helium is coming in from the solar wind. In fact, the helium abundance in the upper atmosphere is maximum in northern winter when the sun is closest. Now, we know that helium diffuses very fast. You get a rubber balloon and it's down the next day. Typically, a rubber balloon loses much of its helium in just one day. Now, we have measured the rate at which helium escapes from zircon. It's very, very high. The old Earth model, the one that says that the Earth is millions of years old, has to have a diffusion model that is wrong by a factor of 200,000. The rate of decay, the rate of escape of helium from the rocks, they say, in order for their model to work, is 200,000 times less than it really is. Okay. Helium diffuses so fast that helium should have long ago escaped the zircons and the rocks. This shows that the decay happened quickly and very recently. For the helium to still be in the zircons, the age of the Earth must be less than 14,000 years, depending upon the original helium content of the atmosphere. Radiometric methods suppose that the radioactive nucleus is an isolated system. Every nucleus is supposedly an isolated system, just sitting there as a clock on its own, doing its own thing. And it's supposed to have a constant decay rate, unaffected by outside influences. But helium is still in the zircons, showing that the decay happened very quickly and very recently, perhaps during the creation week or during the Genesis flood. Thus, nuclear decay must vary. It must vary. Nuclear decay must vary to be in agreement with this. So there's a fifth reason. There's credible research experiments over many years that show that radioactive decay does vary. Radioactive decay does vary. Radioactive decay does vary. With the sun's distance, and solar X-ray events and gamma ray bursts from distant galaxies. This is the variation of radiometric decay of radium-226 over a period of years, 14-year run. And the red is the inverse square distance of the sun. Notice that it correlates exactly. Wow. The sun distance correlating exactly with how the radioactive decay works. The same thing goes for the silicon 28 and going to chlorine 30 and so on. This is three of these events, three of these different kinds of nuclear decays, all synchronized with the distance from the sun. This is another one. This is from Russia. They have the same results. Now, this is the thing that I use to indicate the cosmic ray events, cosmic ray bursts, cosmic gamma ray bursts are involved in this. See the red arrows? Every one of those red arrows is a cosmic gamma ray burst. Notice that there's one right here in agreement where there's no change in the sun. There's changes in the sun here, producing this effect, but there's nothing on the sun doing this. That's the cosmic ray coming from galaxies far away. So we have gamma ray bursts from galaxies far away, and they are affecting things. Now,